Thank you and good morning. So I will briefly discuss about some of the work what we have done, and before that I will also give you some basic introduction of DC microgrid and how robust control techniques can be used to solve various problems in this particular domain. So I will discuss only two main things like after introduction on DC microgrid and what is the control structure. We will discuss about second order harmonics and cyber attack detection in DC microgrid. So in both the problems we can use sliding mode control to solve these problems with uncertainties and external disturbances. So if you see the entire power system, it is actually the conventional model in which we had centralized bulk generation and that is transiting. It has significantly changed from what we had earlier, and the new model in which we have a consumer as well as small generator located in a proximity. So the new emerging model requires that your generator as well as your loads which are very close to each other, rather than generating the entire power at one single location or to the few locations in entire system and transmit that power to long distances, fine. But the model is changing, so you still require centralized generation, but the amount of power you generate that can be significantly reduced and significant power can be generated locally. So this is a new model which is actually giving rise to various microgrids, and these are actually reality. So large number of microgrids are already operational throughout the world. So we are not talking about some future things, but we are talking about something which has already happened and it is continuously growing at a greater pace. So if you look at the scenario in India, that is also quite encouraging in the form of percentage of renewable energy, which is installed capacity is continuously rising. So but still we have a 50% share which is dominated by fossil fuels. Of course, you all have gone through lots of controls, so I don't want to give any basic introduction of control, but you know that we in this presentation we will talk about regulation problem in which we are trying to regulate a particular variable of interest to a required quantity. See, microgrid is a very typical distributed system. It has multiple power converters which are actually physically separated from each other, and sometimes the distances among them maybe hundreds of meters to couple of kilometers. And I'm talking about the microgrid setup, not the actual power system, where it can be like hundreds of kilometers also. But in case of typical microgrid, you can have a significant distance between the converters. So you have a one physical layer in which the individual converter is there, but when they are working as a microgrid, so they have to communicate with each other. So you have a physical layer, then you have a cyber layer in which the communication takes place, and without communication they cannot properly function. And then you also have a certain control layers, like you have a primary and secondary control layers. So primary control layer is the one which is actually co-located with the physical converter, and the secondary controller layer actually decides that what should be the various set points for different converter. So it decides, and you can also have some more layers. Sometimes you can have a tertiary layer and some higher level layers, but the time period of these higher level layers will be much higher compared to the time constant of lower layer. They work in the range of millisecond to microseconds, and as you go up and up, the time segment in which they work that will be continuously, because they will be incorporating more and more optimization based algorithms. So the time scale at which the higher layers of controller work, that will continuously of higher order. Okay, so our interest will be at least on two layers, because for proper functioning of any microgrid, you require at least two layers. One is the primary layer, that is a local controller, where we can implement say sliding mode control or any other controller we can implement. And the other layer what we require is that either consensus layer or Drupe layer or some other layer which actually ensures that power which is distributed by these various converters, this power is distributed as per their respective ratings. So it should not happen that one converter is overloaded and other converter is lightly loaded or may not have any load. Okay, so the dynamics of these converters play a role here. The lines which are connecting the converter, that also play a role here. So the two main problems which we have to address, that loading should be as per our requirement or their respective rating. The higher rating converter should definitely contribute more to the power, and lower rating converter should be contributing less to the power demand. So this loading should take place as per their respective rating. So if you see per unit loading, if you consider, then per unit loading should be same for all the converter. If one converter is giving 30% of its capacity, so all the converters should give 30% of its capacity, or whatever way you wish that a particular converter should contribute. So there are two main things here. The primary control maintains the voltage level, and what should be the voltage level it has to maintain, that is decided by the secondary layer. The secondary layer requires the communication among the converters. Okay, so microgrid also is important from the context of our country as well as many similar countries in which you do not have a 100% electrification in entire territory. So we definitely say that we have a 100% electrified village, but 17% rural households still without electricity. And many times because of the particular location of those regions or areas where the grid-based solutions are not possible. And we need to increase the penetration of renewables. So microgrid is one of the options through which you can actually locally generate and locally distribute. So DC microgrid, why DC? Because we use everywhere AC. So we are trying to say that DC can coexist with AC, and large number of loads are actually DC as well as DC compatible. So it is possible that we can have a hybrid microgrid where you have a AC option as well as DC option. So you can connect your AC loads as well as DC loads. And the advantage here in case of providing the additional DC lines, that your efficiency will be at least 5 to 6% higher than the AC counterpart. So that is one, and many loads are actually DC or DC compatible. So this, and there are situations like if you consider the vehicular power supply or aerospace power supply, so that also creates the DC microgrid. And in that you have multiple loads as well as some sources which actually supply the DC power. So there are situations in which the DC microgrid naturally occurs. Even electric ship, in that also the power is electric ship also has a DC alternate, and in that case it creates the DC microgrid. So there are several applications in which the DC microgrid is naturally created. And there are applications in which we can actually provide the provision of DC supply, and that leads to DC microgrid. This typical DC microgrid, and I will have a multiple converter, multiple sources. They can be renewable or battery or any other kind of source. Then we require communication layer, that's a cyber layer, and I will have a multiple loads. These loads can be non-linear also. I can have a single phase inverter based load, which will inject the harmonics here, and we can actually create a control mechanism through which we can distribute these harmonics uniformly among the converters, or some converter which can absorb more harmonics, and some converter may not be capable of absorbing the harmonics. So that is how we can actually manage this particular problem. See how to, if you consider like say I have two sources which are connected in parallel in DC microgrid. So how to handle them? Like the two things which I need to do is that voltage regulation and load sharing. So voltage regulation and load sharing are the basic problems which I have to address. Then it will function as a microgrid. Fine. Otherwise one will be highly loaded, other will be lightly loaded. So that will not create a microgrid. So you will also have several issues when you are considering these practical systems. You will have a noise which is added in the sensor, then cable resistance, influence of regulation and load sharing, which will be affected by all these things. So one there are also options in which you can have a centralized way of handling these issues and also sharing the power. But centralized issues, a centralized way is actually prone to single point failure, and to avoid that, the solution which is widely used is the distributive method, and group control is one of the methods in which we really do not require even communication among the converters, but with the group they can perform. Okay, so if you consider just two converters, and these two converters, see what we need to do as the load increases, then I need to reduce this terminal voltage. If I do not do that, then that can actually lead to instability in my overall system. So with increase in load, the basic requirement is this should reduce. So I can actually use some virtual resistance RD1, RD2, and that can actually give me the set point, like as load increases, then what should I do? How should I get my new reference? So the basic fundamental here is like, if you do not want any kind of communication between the two sources, then as voltage increases, then you reduce, as load increases, as current increases, then you reduce the voltage. But there are situations why we require robust control here, because you have a cable resistance which you really do not know, and other factors which can affect, and sometimes this can significantly change the load sharing among the converters. So like here we are showing the effect of cable resistance. In one case it can shift the set point from right to left, and in another case it can shift from left to right, so that between the two set points there will be significant difference, and that can actually lead to underutilization of one converter and overutilization of another converter. So for all these reasons we need to have some kind of robust control. There are other methods also in which you can consider. See, droop method ensures that as your current increases, your voltage decreases. So these are the basics of any microgrid, DC microgrid. But you also have a non-linear droop in which the reference can be determined based on load current, and so that can give you the better regulation as well as proper power sharing. Because droop has one disadvantage, that if you go for say better regulation, then you have to compromise with the power sharing, and vice versa. If you want better power sharing, then you have to compromise with the regulation. So so there are non-linear droops also available, and but ultimately all will be affected by the uncertainty as well as cable resistance, which are actually not known a priori. So if you see the typical implementation of any droop, so this is a local controller. So this is a primary controller, but the primary controller will get its reference from the secondary controller. The secondary controller will take care into account what is the output current, as well as in some secondary controller will also take care like what are the neighboring converters are doing. So what is the neighboring converters load, and based on the consensus you generate that reference for the primary controller. So this is the basic structure. So this voltage controller and current controller, this can be PI controller or sliding mode controller. So there are multiple options exist for this local controller. Any control methodology can be utilized. So of course sliding mode gives you some advantage in terms of handling the uncertainties, at least match uncertainties. And so here the secondary controller normally used is a consensus base, which requires communication at least from the neighboring converter. And if you see the overall structure of any microgrid, you require at least two layers. The primary layer, which will be doing the most of the job, and it will be operating in the time scale of milliseconds, and the secondary controller, which will be providing the reference to the primary controller. Sometimes you also have a tertiary control layer, which will do the power flow management, energy management, some high level things, and that will inform that what should be the various set points and references for the primary controller. So this is how it handles the overall structure. So this is completely distributed system. So you have a nodes which are, if we consider one converter as a node, then it is actually distributed by hundreds of meters. So this is completely distributed system, and subjected to different kinds of uncertainties. So one possible uncertainty coming from the load, which is always varying in nature. The other is the various parameters of the converter itself, as well as line parameters, which are many times a priori not known, and there are significant variations in that. Okay. We will just take very brief overview of the entire structure before we go for the main problems. So the basics of graph theory, I hope most of you know about that. If I have a set of nodes which I define as V1G, V2G up to Vng, and set of EGs can be given by Vg cross Vg. So this is available in this particular set. Adjacency matrix we can define as Aij, and Aij will be greater than 0 if this age is available in Eg, and otherwise it will be 0. We can mostly we will take Aij to be +1 if the node I and J are connected. Otherwise we will take it as 0, right? And I believe that most of you know the Laplacian matrix, that is D minus A, and the eigenvalues actually determine the global dynamics, and Dig is in degree matrix. If the symmetric graph is there bidirectional, in that case you will have a in degree and out degree both identical, but just for the completeness, Dg represents the in degree matrix. And of course, for this kind of graph you can obtain Ag, and this is L. So D minus A will give you L matrix, which is diagonally dominant matrix. And okay, so this is the typical structure. Again, you have a control layer, cyber layer, and physical layer. And so we will discuss this before we go for the main problems. and just trying to develop the background. So what happens, a particular converter actually transmits a set of data. So that data is because it is a microgrid and DC microgrid. So my main control variable is the bus voltage. The bus voltage which is seen by a converter, because converter will see at the output terminal what is the bus voltage, and that bus voltage it will try to maintain. So, and also it will try to calculate based on communication from the neighbor that what is the average bus voltage. So every converter, every node, we will consider that converter as a node. So every node will have its own value, as well as it will have its own measurement, that is Vi, and it will also have an average estimate on the entire DC microgrid based on the neighboring value. So that Vi bar is the average, Vi is the actual value which is measured by it, and this I per unit, this is the per unit load current contributed by that particular converter. So it knows only its own load current, whatever the current it contributes, and that is given in per unit, so that we can compare the current of one converter with another converter, because what happens that rating may not be same for all the converters, so that when we convert into per unit, it is easy for us to compare. So per unit is obtained based on the respective rated current of that converter. And so this every converter transmit this information through a communication network to the neighbors. And so this actually consist of estimate of local average voltage of microgrid, and measured value, and this per unit current. So per unit current can be obtained in this particular way. So I rated is the rated current of ith converter. So what is the objective of secondary controller? See, primary controller, we know that it can be PI, it can be SNC, or any other methodology you want to use depending on the requirement of that particular problem. And what we can do here, that now if we consider secondary controller, so what is the job of secondary controller? Secondary controller provides a reference to the primary controller, but how does it calculate that reference? So the secondary controller has to do two things. The global voltage regulation means there is a microgrid, there are impedances also between the converters, and because of that you need to maintain certain global voltage regulation, and because throughout the bus you do not have identical voltage because of the presence of impedance. So therefore you will add one converter will see some voltage, another converter will see some other voltage, but ultimately the average of all these voltages should be within certain requirement. Okay, and the proportional load sharing. So these two objectives are to be met. So how do you met? Ultimately, what secondary controller gives to the primary controller is nothing but the set point. So that set point should include all these requirements. So there is a one global reference. I means the particular node. So I can be 1 to n depending on how many nodes you have. And so for every node, Vi star is the reference, and this Vi star can be obtained by one global reference, which I require. Say I want that the voltage should be 380 volt DC. So that is what is the global reference. But you may not be achieving that global reference, but you will be getting somewhat closer to that because of the structure of this system. So then the second is this part is nothing but the droop, because as you know that as the current increases, this is the load current of that converter, then the voltage should drop. So if suppose the entire communication fail, then also the system should work, and that is why this particular term is there. So this will initially, because you do not have any other information, so when it starts from the cold, it means that starts from the zero, it will be only using this particular information to generate the reference. But as you then there are, this is superscript, this is 2 is not a square but superscript. So these are the two correction terms. These two correction terms are added for actually eliminating the this first correction is added to eliminate the discrepancy between this average voltage and Vi ref, what we are providing here. So this can be PI controller or it can be any other form of control. And the second is actually second correction term. So first correction term is to eliminate the voltage discrepancy, and the second is for ensuring that equal load sharing. So that is actually generated based on consensus, and because these converters communicate with the neighbors, and based on that you can calculate this delta Vi2, and this 2 is a superscript, not a square. Okay, so based on this, so this Vi star contains all the requirements of the secondary controller to meet the global voltage regulation. This is through this, and proportional load sharing, this is this, and this is what you require. That ideally I should have this value, but many times it is not possible, and this term is added just when the entire communication fails, then still system should work. So that's why this term is added. So this will work whenever there is no communication. Okay. The secondary controller actually produces these two correction terms. So the first correction term based on the voltage reference, this is the Vi reference for every converter, and there is a consensus based voltage observer which will calculate the estimation of Vi. What is the estimation observed by a particular node I, that is Vi bar. So this uses the consensus based algorithm, and based on that it actually provides value here Vi bar, and our objective, this controller objective is to eliminate the difference between these two. So it can be done through PI controller or any other controller, and you generate this correction term. This is taking the input from the neighbors also. So depending on the topology of your converter, so every converter have a say 2 or more than 2 neighbors, or depending on what kind of topology you have, so that will decide. So the second correction term is this consensus protocol, in which what we try to obtain that Vi, the estimation of average value of voltage for every node. So Vi bar will be obtained here. So Vi bar is obtained based on this consensus algorithm, and we can also prove that ultimately finally I'm not going into details of proof, but this is a very celebrated consensus based observation algorithm. And what we can do, we are saying that in our case we are saying that we require communication from the neighbors. Fine, we require only that communication, and we have a spanning tree in our graph. That is the only requirement, and with that we can actually establish that this final estimation, this Vi bar, if I put in a vector quantity, so this Vi bar will actually contain all the values V1, V2, V3, Vi1 bar, V2 bar, V3 bar. So this is what written in vector notations, and so So what we can prove that finally the steady state value will be nothing but the average of it, because Q is a matrix in which you have this 1 by n values. Each entries of this Q matrix is 1 by n, and total number of node is n. So that's why it will reach to the average value of voltage measurement by all the nodes. Fine. So finally, the steady state value of VSS will be this. So that is what we can prove with using simple standard arguments. And so let me go to the next. We also, because we have a multiple converters, we have an n converter, so we need to develop the overall model also. So when we are developing the overall model, so we right now I am just explaining with the simple PI controller, where the delta V1 and delta V2 are nothing but the your voltage error PI controller and the current error PI controller. This is obtained through consensus. That's why you have a Laplacian matrix L. And so with that we can develop the overall model. If you see that if I write this entire equation in a vector form, so my overall model will be something like this, by putting the respective values of delta V1, delta V2, and using the standard arguments we can actually develop the overall model. And we also use the local controllers. So because whatever V star we provide, ultimately the output voltage will be V times the V star, depending on what local controller I am using here. So by putting those values, the final model which I will get here is this. These are existing results, so I'm just trying to go slightly fast on all these things, so I can get the final model. And we can prove if my local controllers are stable, then I can, because local controllers we can design so that it remains stable. And with that we can say that finally what will happen, that overall system will actually follow this my reference, and so my steady state value will reach to the reference. That is what we can establish. And finally we can say that my steady state value will not will be something which is equal to V reference, right? From equation 8 we can say. And what we are using is only the observer, that is consensus based observer, local controller, which are designed to be stable. And this local controller also need to deal with nonlinear dynamics of power converter, because large number of converters actually result into nonlinear dynamics. So local controller, you have a multiple options to design so that they remain stable. So that is the only assumption in entire analysis. So finally we will ensure that our steady state values of each node voltage will reach to the corresponding reference. And okay. So the same thing we can say about the current. The current will also be distributed. So let me now go for some problems. So what we have learned so far is, like, I need a primary controller, I need a secondary controller. So this primary controller will obtain its reference from the secondary controller. So secondary controller will provide that where the primary controller has to reach, because primary controller is essentially nothing but the voltage controller, and it is controlling the voltage. But where it has to keep that output voltage, that is calculated by the secondary controller. And secondary controller takes various things into account, like load sharing as well as global voltage regulation. So there can be some more things. So before providing the reference to the primary controller, it actually calculates all these things, and based on that only it calculates the reference for the primary controller. So these are the two things which I want your attention to. So that is how this entire structure is working. So now let me explain you what happens when we are taking the AC load from DC microgrid, because many times you require to have this kind of single phase AC load. So like this is a see, there are multiple sources here. There are DC to DC converter here, and then they are connected through a bus. And because there is a line resistance, that's why every converter does not see the identical voltage at this particular point, but it will be in a very small narrow range. So average value of voltage which you try to regulate. But one problem which occurs when you have a DC to AC conversion, it will actually inject the second order harmonics, and that too very significant quantity of second order harmonics, because you are converting DC into AC. So AC power is pulsating, and this the second order harmonics which actually penetrate to the source, that creates problem. That creates a problem in the sense like it can go to a source which are really not equipped to handle that kind of second order harmonics. So they are not designed like fuel cell kind of source or PV kind of source, which is really not equipped to handle such kind of second order harmonics that can severely damage that. So what we can do, the control allows us to introduce the virtual impedance at various frequency. So if I because in India we are using 50 hertz, so our the second order harmonics becomes 100 hertz. So what we can do, that suppose some converter like this converter, this converter is unable to handle this second order harmonics. Through control technique, I can introduce very high value of impedance here, like at 100 hertz only. So at 100 hertz, if my impedance is very high, so there is no way it can penetrate here. So I can control the entire system in such a way by introducing this impedance at 100 hertz, which is very high. In some converter, it is low. So the entire second order harmonic which is generated at the bus, everything will pass through this converter where you have a low impedance, and your converter which are having the high impedance, they will not be allowing this second order harmonics to pass through. So you can protect those sources which are actually meant not to take the second order harmonics, fine, because it can severely affect, particularly battery, PV, fuel cell. These kind of sources are also in use, and particularly battery and PV, they are very commonly used, and they get severely affected by such kind of second order harmonics. Okay, so what we can do, but at the same time you also need to ensure that power sharing is equal, and also need to handle this second order harmonics. So if you see the basic concept, the AC power we always say in terms of VAC by IAC, and if you further analyze and decompose them, then you have a constant component and variable component. So you have a PC plus PR, and so this power has to be shared by n parallel converters which are connected in parallel. And so this is not only like, this is a total load, AC load, which is demanded in the DC bus at by DC to AC converter. And that's why when you are converting this DC to AC, you always generate this, and it has the same magnitude. If you see this equation, they have the same magnitude. So this ripple power, what we call it, that is very almost same value whatever your active power is demanded by the load. So how to handle this particular thing? So so let's do some transformation. So we will actually use per unit values. So for per unit values, you can say ICI per unit value, IRI per unit value. So I am dividing it by some base current. So the per unit allows me to compare the current of one converter with another converter. So that's why we are converting into per unit values. So all the currents are per unit. So you can easily compare the current of one converter with another converter. So let's define this gamma 1 to gamma n. They are this is the maximum current. IM is the maximum current, and with which we are dividing this. So we are defining this gamma 1, that IR1, and this IR2 by IM is gamma 2, and so on. Fine. So so what we see, please understand that this ripple current is IR, and the actually constant power component is IC. So R subscript we are using with the ripple current, and the C subscript we are using with the actual AC current, which is flowing in the constant component which is flowing in the in your AC side. Fine. So so this is the ripple, which is this ripple current. We are interested that ripple current should not be shared equally. We are interested that only some converters should absorb this ripple, because this ripple is required. So you can't deny this. You have to provide this ripple. But how do you distribute this ripple, and how do you ensure that it will be only absorbed by some converter? For that, we need to design a proper control system in which we have to ensure that we do the impedance modulation, and through this we can actually achieve this ripple distribution. So this gamma 1 to gamma n, the total ripple requirement will be, because now you are going for per unit, so it will be 1/2 cos twice omega t. See from this particular PCR VDC by IR. and through this you will get because we are assuming that Vm is equal to VDC, that's why we are getting this VDC cancelled from both the sides, and in that case what happens, the total ripple is nothing but 1/2 cos twice omega t. So because we have gone into per unit, that's why we are getting rid of these absolute values, and so this power is a summation of ripple power of all the nodes. So what we want to do, that suppose in some case I want that this converter 2 should not take any ripple, fine. Suppose one of the converters, suppose the SRC means second order harmonics component here of any converter say at node 2 is to be mitigated. So this should be made 0. In that case, what is my equation, that I want that this is I2n but not I is equal to 2. So this summation should be 1/2 cos twice omega t, but this will not now contribute any ripple. So how to achieve this kind of objective? By designing the proper primary and secondary controller, because what is in our hand is only primary and secondary controller. That is what we can design so that we can achieve our this additional objective of ripple distribution along with the distribution of load. Fine. Okay, so if we see the modeling of this converter, so if ith converter, this is a second order system, and what happens here, that this is a bilinear system. You see that this input is multiplied with state. So VC I and ILI both are the state. This is the capacitor voltage and inductor current. So here these are all bilinear system. Whenever you have any boost conversion at that time, this resulting equations which will be bilinear. Bilinear means state and input both are getting multiplied. And what we can do here, if the state variable, because we are interested in error coordinates, so because we know that where we have to reach, that is VI ref, and so an IL ref, II ref I know. So what we will do, that we will convert this equation into error coordinate so that we can directly work on error coordinate, because our intention is to make that error 0. So now these equations are in error coordinate, and so primary control what we are using is adaptive sliding mode controller, and secondary controller what we are using is the dynamic consensus based control. But this adaptive sliding mode control ensures that your ripple is distributed the way you want it to be. So so adaptive switching sliding surface, if you see that is because it's a second, this is a local controller what we are designing, so that for that the switching function is rho I e I I. These are the error in current, and this is error in voltage, and this alpha is also not a constant term, but it has to be obtained based on the load, so that we will see in the next slide. So this alpha is to be obtained. This is a nonlinear function. So eta is some positive constant, and VCI, this is the error between this your state which is capacitor voltage, and beta I is some positive constant. So if you see that depending on your load, you are actually changing this alpha I, and we can prove that even this nonlinear surface with the nonlinear model, that stability can be guaranteed, and so the profile of alpha is given here. So when it should be high and when it should be low, that is obtained from this particular graph, and this will actually ensure this rho I will allow us to actually modulate the impedance, and the particular value of rho I will ensure that you have a high value of impedance for second order harmonics, and for some converter you can keep rho I small. And this is the secondary controller, which is the same as what we discussed earlier, but it has a this sharing term available here, and of course this term is a standard term which is similar to your droop, and but that is obtained from this particular value. This takes into account of this current from the neighboring. So this is the DI. So these are the two controller, like the primary controller is the sliding mode controller, and we are using the first order sliding mode, and the secondary controller is actually taking into account of the current distribution and voltage, and the sliding surface is nonlinear in nature, and the controller dynamics we can obtain. This is the first order. The advantage with the power converter is that controller itself by nature it is discontinuous in nature. So even we can give only 1 and 0, that is also one way to control. But if you want to go for PWM, then also you can actually obtain the PWM variant for the control. So this is what is the control value. So it will have a signum function, means discontinuous part as well as continuous part, and this is derived based on this particular reaching law. Okay, so the main innovation takes place through the nonlinear sliding surface, which meets all the objectives in terms of variations in impedance. So for proving the stability, we can use the Lyapunov method, and we can actually ensure the stability. I'm not going for the complete proof, but these things are documented in our papers, but we can use the Lyapunov to prove the stability. And we can prove for all the nodes together by taking the Lyapunov function, which is taking into account all the nodes. So we are proving the stability during sliding mode, because during sliding mode it becomes a second order system will become first order. But we have to also keep into mind that our dynamics, we are not doing any linearization. The dynamics itself is nonlinear, and we have to establish the stability with this nonlinear surface and nonlinear dynamics of the converter. So then proportional current sharing is actually happening through this consensus based, so distributed consensus based control. We have already seen the secondary controller, but just the philosophy behind that is provided here. So this consensus based controller IJ per unit, this value is utilized in our secondary voltage reference calculation, and this is how we calculate. Of course, this is already known and published thing in the literature, because this kind of consensus is widely used in various applications. So we have only used this consensus to ensure that our secondary controller actually provide the reference corresponding to equal distribution of current for all the converter. Okay, so we can also see that this is a dynamic group, so it is not a constant, because if the load changes, then this group changes, and this is how you can see that in our reference. If I again open that equation, this DI. So DI is not a constant, which is normally used as a constant, but we are using this DI, calculating DI based on the current distribution. So the dynamic group, you will have a close, but if you go for this dynamic group, then this is the experimental results, and you will get the very almost same. Fine, there won't be any deviation in the current. All the converter, because there are 3 converter, and all the 3 converter currents are overlapping. And with this inverter load will actually inject the second order harmonics. So you can also ensure that all the 3 converter are actually taking the same second order harmonics, but it is programmable. So you can say that one converter. So if you see our experimental setup, we have this boost converter 1, 2, 3, and some AC bus we have, inverter also we have. Then this is the lamp load, and this is the Opal RT through which we implemented the controller, because we need to control 4 converters here, 3 boost converter and 1 inverter. So 4 controllers are implemented in this Opal RT, and if we see some of the results, and these are the calculation related to various parameters which are required. So I will just skip and come here. So see, when you turn on the inverter, then you see here that all are actually taking the same ripple current. Fine. Why it is oscillating? Because there is a 100 Hertz ripple, and that's why they are oscillating. These are the oscilloscope plots, and so this they are actually taking the same. This is having both the thing, DC component as well as AC component, but you can see here that this all are same. They are completely overlapped on each other, and all the 3 converters are sharing the same current. But it is possible for us that, see, out of these 3, only 1 is taking this entire current. Fine. So that is also possible that we can only so these are the rho values of this sliding surface. By modulating the rho values, we can say that which converter will take more ripple and which converter will take less ripple. So this ripple at 100 Hertz we can modulate through this. So only one converter is ripple is reduced for converter number 1 and 3, and second is taking all the ripple. Fine. So that also, but they are sharing the same DC. We have to understand that we are not compromising in this DC sharing, but only we are modulating this AC part sharing. So you can see here that in SRC is increased here, like SRC means second order ripple. So it's second order ripple component. So this is second order ripple current. So that that is increased here, that is decreased here. So here it is kept constant. So for one converter, so we can actually modulate a rho value in the switching surface parameter and decide that how much ripple will be carried by one particular converter. So because of the sliding mode, you will get also robustness with respect to match parameters, and the system will function as if there are no perturbations present in the system as long as these perturbations are matched. Okay, so now I go for this second part in which we will use the sliding mode observer as well as functional observer to detect and mitigate the cyber attacks in DC microgrid. We have already seen that we require communication. Without communication, this controller will not work properly. So, or you will not get the benefit of equal power sharing and many other things if you do not use the communication, because there are results without communication also. That is the typical truth-based results. But because of the ubiquitousness of these communication protocol, communication resources, so we can always use the communication to make it better, because we require communication only between the neighboring converters. And let's consider there are 4 nodes here, like node 1, node C. You can see the back side is one more node. So there are 4 nodes. So where the cyber attack can take place whenever there is a communication channel, because what happens here, that controller receives the information through some communication channel. Controller also sends this information through some communication channel to produce the specific PWM. Certain things are air gap. It means there is no way that intrusion can take place, but there are options through which the intruder can actually attack the system, because this controller is also connected with the other network. So it is possible that even whatever is going to the controller, that can be modified, and in that case the attack can take place. So how to mathematically model that part also we will see, but see, one possibility is like whatever the actuator values are calculated, so that ultimately in power converter you have to provide PWM, or if you can directly go for completely discontinuous kind of control, that is also possible. But typically what we do is the PWM. Even with the sliding mode we do with the PWM. So what can happen, that this PWM, whatever values you are calculating, that can be augmented by the attacker in a way that many times you can't even know that it is augmented, or sensors can be attacked, and there is a possibility that you can also attack multiple sensors. So there are different kinds of attack which can take place, and so this is also false data injection attack. And when you are attacking, so we will focus only on the actuator attack. So is there any way that whatever the controller, whatever the value we are calculating based on the sensors, whether we can calculate independently, so that we can have some kind of verification and some kind of signature generation in case there is an attack. So the rest of the things are same, like you can have multiple loads on this, and also you require other control strategies as it is, but you will have one more layer which is completely dedicated for detecting this attack. So see what kind of difference, if you want to model this, now it looks very similar to say attack which are taking place. If you see, mathematical model is very much identical, but nature is not that identical. And so if there are attack which are taking place on sensor or measurement, so that can be modeled in this particular way. So the red part is if it is LTI system, then you can actually model in this particular way. So you can have a false data injection attack. Many times you have a denial of service attack, replay attack. You can have a stealthy attack, which are very difficult to determine or detect. So there are multiple attacks which can actually take place on plant. So we will only focusing on false data injection attack, and that is also on actuator attack. And so what we can do here, that our architecture, what we are considering right now, even for implementation, we are considering the 4 nodes, and what we are trying to do, that we are actually using the functional observer to calculate the value of input, which is actually going to the plant. We are not, and based on the difference of these two, we are generating a signature. We are integrating this thing through a function, and by which we can actually generate the signature, whether there is an attack on the system or not. If there is an attack, then it is possible for us to even operate the system that by switching it to functional observer, so that we are not dependent on the sensor values, and we can directly calculate through this functional observer. So each node is consist of say DC boost converter and primary and secondary control layer. The other requirements will be same. There won't be any change in the other requirements. And so secondary controller, that responsible for proportional power sharing among the nodes, and communication network is there. This is the communication network. So every node is connected with the other two nodes. This is the cyber layer in which we are carrying out the communication. And the basics of linear functional observer, that if I want to observe some function z, which is fxt, so it is possible that you can also observe one single sensor, one single state, if it is possible to construct the observer for that. And many times it is possible for large class of system that you can also have only one single state estimated. But if you want to say estimate state 1 and 3, then this is how you can use your f. And if suppose the same way, you can also calculate your u, which is nothing but the linear combination of states, if you are going for say state feedback controller, or even if you are going for dual loop PI controller, which is widely used for power converter control. That also you can estimate using the functional observer. So PID parameters can also be estimated by using the functional observer. So if you want to construct the function, z is the one function which you want to estimate. So the observer introduces its own state, that is w, and this is what is the observer state equation, that w dot is equal to nwjy plus hu, and z hat is equal to dw plus ey. So you need to ensure that z hat goes to z, st goes to infinity, and for that we need to ensure that these conditions are satisfied. So we have to choose the values of n, j, h in such a way so that these matrix equations are satisfied, and that can be designed. So that this theory is already well established, so I'm not going much. But we are using this observer. We also have used the sliding mode observer, sliding mode functional observer, to estimate this u under a robust environment. So what we are trying to do here we are using this observer to detect the attack, and also use this estimated value of u to run the plant, even the plant is subjected under attack. But attack is only on u, fine. So if it takes place on sensor as well as on u, then it cannot be used. But if attack takes place only on the actuator, then you can run the plant without any kind of difficulties with the u hat, which is estimated from the observer. So the sliding mode, then we also use the sliding mode functional observer, in which we are adding this signum term, which introduces the extra robustness. And so this is also existing, and this work is already existing. We are using this particular observer in our work here to observe to reconstruct the u in a robust setup. So parameter variations and other things will not be affected. So for this, we also developed a finite state machine based model. So FSM based model we developed here, so that you understand that in which state you are. There are multiple states. So you go from one state to, because there is a healthy state, there is a attack state, and you are also running, but you are in an attack state. So to differentiate in which state your machine is working, so we have developed finite state machine based model for sliding mode functional observer, and also we use the linear functional observer without sliding mode. And so the basic principle here is if you see that for ith converter, what we are doing, that our secondary, this is what is our converter. So here we need to provide the input file. So it will go to your power converter. So the input is coming from this dual loop PI controller, which is widely used for that. This is the primary controller, this is the secondary controller. So this dual loop PI controller, we can estimate this entire dual loop PI controller, we can estimate through the functional observer, and it also calculates say U1 hat. You can see my mouse pointer. No? So this UI hat we are calculating by using this functional observer, and this UI is coming from this dual loop PI controller, and this goes to PWM. So if there is an attack here, if you detect in some way that there is an attack on the system here by on actuator attack, so I can switch from UI to UI hat, and I can still run the plant. Provided there is no other attack except this actuator attack. So that is what is the advantage of using this thing. So if you see the system modeling for the ith node, now we are also modeling along with this dual loop PI controller. So the total number of states will be 4. The 2 states are additional state which are introduced by the controller. So they are the flux state and charge state. So 2 extra states are there. So here to design this, we are going for the linearization, because again this is a nonlinear bilinear system in fact, and we are linearizing this system about the operating point, and the linear dynamics is represented here, that the delta dynamics represented here, and so we are designing this. So our controller becomes this. So controller is not designed by sliding mode, but controller is dual loop PI controller, and the observer is sliding mode functional observer as well as linear functional observer. But the main purpose here is to ensure that how we can use functional observer to detect attack or even fault, because this similar situation can also occur in case of fault. So both the things we can reconstruct here, and this is the algorithm through which we can detect, and here we are providing the finite state machine based model, so that you have a you know that in which state machine is operating. So there are multiple states, 4 states are there. So healthy state, attack state, and the state in which it is just waiting to detect. Whether the first time when it detects, it will not immediately act, but it will see that multiple times. So our signature through which we are actually generating this attack, because it is not whenever this is crossing some threshold. So this is the difference between that, and we are taking the square and integrating for some times in some window. So whenever it crosses some threshold, we are again checking, we are again resetting this function to 0 and again checking. So if this happens multiple times, then only you can determine there is an attack, because there is no mathematical way to determine there is a attack. So because similar kind of situation can occur because of multiple other situations like parametric variations or external disturbances or sometimes load variations. So because of that, we need to ensure that we check it multiple times before we take a call. That so that is also determined heuristically, that how many times you have to allow this function to cross that threshold, and then you now designate there is an attack on the system. So we have developed this algorithm which can be utilized to determine this attack, and similarly we did this experimental verification on that. And if you see, we are running this system even under the attack. So the attack actually took place on node number 4. So you can see that this attack is actually completely changing this current I4. There are 4 nodes which are working, the other nodes are healthy, and so at this time you see that this is that signature. So it has crossed again, it is reset again, it has crossed. So it is continuously integrating, and it is checking whether it is reaching to that threshold. So when it reaches this threshold multiple times, so that time also you decided how many times it will be allowed to reach to that threshold. And based on that, you take a call that now it is attack. So now you switch to, you are switching to U4 hat for node number 4. So again, after some time, it will stabilize to the same value, which was there earlier, 5.3 ampere. So after some time, it will reach to the same value. Other nodes are not affected, but U4 will be definitely severely affected because of this node. But U hat 4 is not affected. Even during attack, it is not affected, and this remains healthy, and it can actually replace the U4. So So this is how it can, we have also verified when the attack is happening on two node, not only one node, like two node number 4 and 1, but still you can actually bring the system to a healthy state by switching to that respective U14 and U4 hat. And so here also you can see that whenever the attack takes place, you can actually determine at this particular instance and then again go back to the healthy situation. So this is your I1 and I4. So some bus voltage fluctuation you can see here, but otherwise you see that bus voltage is largely normal, not getting much affected, and this current also becomes normal after some time once you switch to the your estimated value of U for a respective converter. Okay, so then there are multiple situations in which we also check this observer, in which the sliding mode functional observer, and we gave a lot of parameter variations. We only just posted this switching function part of this sliding mode observer. So you can see that when there are parametric perturbations, we are using the different values of capacitance, but still this is estimating the correct value. So our estimation is not getting much affected. U4 hat, which is estimated by sliding mode observer under significant noise, which was contributed by, which is added deliberately to the sensors, but this is not much affected. And the same thing for this is the I4, which was added with the noise, but your estimation is not affected. The same thing is also here. Capacitance was increased, but fluctuation was within just 5%. Whatever the was used in model and what was the actual, that there was significant difference here. So that this is how we introduced the parametric variations, but the U4 estimation was not much affected. So very little effect was there on U4. So just to ensure that this sliding mode functional observer is robust against the parametric variations, we tested against some variations in terms of noise as well as some parameters which are very likely to change. Normally inductor values are changing only at the time of saturation, but capacitance also has a aging effect, and even some other environmental parameters can affect the capacitance values. That's why we gave the capacitance variation and tried to see how U4 estimation is affected with that. So this is the setup what we created here in IIT Jodhpur, and I'm really grateful to my students, Dr. Suresh, Nupur, Aditya, Manisha Bandari, Shivam, Mohit and Rahul, and of course funding agency DST, MNRE and Maiti. So thank you all.
Long live India and France friendship.